So my name's Steve Parks. I'm with a company called STAR-Dundee from Scotland in the UK. I'm going to talk about next generation of spaceflight processors that we're working on with ATML. Okay, so this is an overview of the talk. First of all, I'm going to talk about SpaceWire. I'll then just introduce STAR-Dundee briefly. I'll talk about the processor chip we're working on, which is called Castor, describe its capabilities, and then just run through some of the applications that we're targeting for this flight processor chip. Okay, so could maybe have a show of hands of how many people have heard of SpaceWire? Okay, so that's great. I'm really pleased about that. What about people using SpaceWire? Okay, so that's good too. Great. Okay, so we work very much on SpaceWire technology. SpaceWire is a computer network technology for use on board spacecraft. It connects together the data handling elements of the spacecraft, so the instruments, the processors, the onboard mass memory, the telemetry and telecommand system. It's a standard interface. It's simple, which was one of its driving principles. The implementation requires few logic gates. It's high performance and it has a flexible architecture. The SpaceWire standard was written by the University of Dundee with inputs from international spacecraft engineers. Currently it's being used or designed into well over 100 spacecraft, worth well over $15 billion. And these cover scientific exploration, Earth observation, and commercial missions. The technology from Dundee's been, SpaceWire technology from Dundee's been designed into USA, European, Japanese, and other spacecraft as well. So this gives just a picture of some of the more notable missions that are currently using SpaceWire, including missions like James Webb Space Telescope, SWIFT, I think, was one of the Gamma Ray Burst Observatory was one of the first NASA missions using SpaceWire, and so on. So there are many missions. Oops. Let me get my buttons right here. Sorry. Okay, so STAR-Dundee's it's a small company. We incorporated in 2002, mainly to support people that wanted to use SpaceWire technology. Since then, we've become a supplier to NASA, ESA, JAXA, and the global space industry. We're based in Dundee in Scotland. That's the office is the building that you see there. We are certainly one of the leading SpaceWire experts in the world, and we're very much involved in developing the SpaceWire standards. Our staff are highly technical, so over 50% of the staff have got PhDs, 80% of the staff are involved in technical and R&D related activities. Our capabilities include chip design, electronics, software, and obviously SpaceWire networks. We manufacture products, but all of our manufacturing is actually outsourced, so we don't do any manufacturing in-house. This slide just shows some of the products. We have chip designs, IP cores, interface and router devices, and SpaceWire analysis tools. We also work on real-time instrument emulators. We do software for SpaceWire devices, and we also have some flight chip development kits. So one is for the ATML AT6981, which is a SpaceWire router, and also for the ATML RTC chip, the 7913, which is a Spark-based processor. And we actually provide both the hardware development kit and also the software. So we provide software tools for the Leon and related Spark processor devices. Okay, so that's a bit of background. So what about the Castor chip that we're developing? So this is intended to be a complete system on a chip for spaceflight applications. It incorporates a powerful processing core with a floating point unit. It has on-chip memory management. We've got a substantial amount of on-chip memory. interfaces to external memory. There's a SpaceWire router is integrated in the chip as well, together with some SpaceWire protocol engines which offload the SpaceWire data handling from the main processor. We've also got MIL standard 1553, CAN bus, and many other peripheral interfaces. The chip is being designed by Atmel, with STAR-Dundee providing the SpaceWire technology and also the software support tools. It's being implemented in 90 nanometer technology. It will be low power, high performance, and radiation tolerance. This block diagram shows the overall architecture. I'll just go through each of the sections of this device one by one. So first of all, there's the processor. So this is a SPARC V8 processor. It's based on the Leon 2 FT core, which is a 32-bit architecture with a 5-stage pipeline, 8-register windows. There's tightly coupled instruction and data cache, 32K bytes for each of those. There's an integrated memory management unit with 32 table entries and an integrated IEEE 754 floating point unit, which handles both 32-bit single and 64-bit double precision. It provides high processing power, so it's over 100, running at full speed, it's over 150 MIPS dry stone 2.1 or greater than 40 megaflops whetstone performance. And the processor incorporates an AHB bus interface. Okay, so that AHB bus interface connects into this central switch matrix, which connects all of the elements of the processor chip together. So this provides multiple AHB master and slave interfaces, and it dynamically connects masters to slaves. And it can concurrently connect several masters to several slaves, provided that no two masters access the same slave at the same time. And this is actually prevented by an arbitration mechanism. So the masters are the processors and the DMA controllers, the slaves are the memory and the various I/O peripherals. Okay, so now moving on to the memory. There are several banks of internal memory which are attached to the switch matrix. So these are split into several banks so that those banks can be accessed concurrently. And then there's also an external memory interface for connecting larger amounts of memory externally. So the internal memory, as I said, there's several banks, each on a separate slave on the interconnection switch matrix. The total internal memory will be around about 1 megabyte, so there's a substantial amount of on-chip memory. And it's EDAC protected, that's all built into the chip. The external memory interface can support PROMs, SRAM, SDRAM, and various types of DDR memory, and EDAC protection is provided for those external memories as well. Okay, so moving on to the peripherals, we have extensive SpaceWire capability built into this chip. Okay, so as you can see, there's a SpaceWire router and 3 SpaceWire engines, as we've called them there. So the SpaceWire engines offload the processor from the SpaceWire communications. They provide SpaceWire remote memory access support and can operate both as RMAP targets and RMAP initiators. And just so we understand how this works, I'm going to talk a little bit about RMAP. So RMAP is Remote Memory Access Protocol, and it's designed to run over SpaceWire to remotely access memory or registers in a device across the SpaceWire network. So this can be used for configuring and controlling instruments or other equipment and for reading data from them. So I'll just show you an example of a write command, an RMAP write command. So it starts off with the destination logical address, which is a SpaceWire logical address. Then there's a protocol identifier, which for RMAP is just number 1. Then there's a packet type and command. So this would, for the write command, this would just say it's a write command. And then there's a field called a destination key, which I won't bother explaining. Then there's a source logical address, and this says where the command came from, but it also tells you where to send the reply to that write command back to. Then there's a transaction identifier, so that you can actually send out several commands one after the other, and then receive the replies back in any order, and then you can relate the replies coming back to the particular commands that cause those replies. Then there's the address you're going to write to, and this is actually, there's a 32-bit write address, and then there's an extended address, so you can write to many banks. So we can access large amounts of memory with the RMAP command. Then we have a data length, which tells you how much data you're going to write, and we can actually write large amounts of data in one go. So we've got 24 bits of data length field there. And then there's a header CRC, so we can check all this information is correct before we actually start the write operation. Following this, there's actually the data we want to write, and then there's a data CRC. So after writing the data, we can actually check that the data we've written in was correct. There is also in RMAP, there's a mode whereby you can actually write the data into a temporary buffer and then check it was correct before you actually copy it into memory. But that's used for smaller amounts of data. So that gives you an idea of what we have in a write command. It's finished off with an end of packet marker, SpaceWire end of packet marker, so you know it's the end of the SpaceWire packet. Okay, so the write operation works like this. We've got the RMAP source and the RMAP destination, so the initiator and the target. And in between the two, we've got the SpaceWire network. So a user application will do a write request. The RMAP initiator will then send the write command across the network. It arrives at the RMAP target, and that does a write data request to the user application. The user application then gives write data authorization. So you check that if you're writing to an area of memory, you can actually check that you're allowed to write to that area of memory before you get authorization. Then you write the data, you indicate that you finish writing the data, and you can send a write reply, which is basically an acknowledge saying that I've completed that write operation. And then that basically goes back to the user application saying, okay, I've done that. Okay, so that's how it works. This shows the write reply. So we've got the source logical address, the protocol identifier, the command, which is, of course, now it's a write reply, the status, which tells you whether it was successful or not, the destination logical address, so where this reply came from, the transaction ID, so you can actually correlate this reply with the command that caused the reply, and then there's a reply CRC and an end of packet marker. So that's actually what comes back. Okay, so to go back, so that gives you just a brief introduction to RMAP. RMAP has read and write operations and also read, modify, write operations, and these operate across the SpaceWire network. So the SpaceWire engines have RMAP target capability, so they can receive RMAP commands, execute those commands, and then send the replies back. And the memory region, the authorization can either be based on a memory region, so you can say, okay, RMAP is allowed to write into this area of memory, or it can be software based. So when a command comes in, you basically interrupt the processor, and the processor can then check whether this RMAP command is actually authorized for execution. So that's basically protecting the processor from some other unit actually inadvertently writing to incorrect areas of memory. We then have, within each engine, we also have an RMAP initiator. So as I've said, we can actually post multiple RMAP commands. So this can be quite useful. So what we can do is set up a series of commands in memory. And so supposing you wanted to basically routinely do some housekeeping operations. So you wanted to read a number of instruments and just check their current status. Well, you could set up all the commands to do this in memory, and then maybe every 1 second or so, you could say, okay, execute this series of commands. The SpaceWire engine will then actually send out all those commands. It will get the replies back. It puts the data in the reply into a particular area of memory determined when the RMAP commands were set up. It will go through, collect all the replies, and only when it's finished collecting all those replies will it interrupt the processor and tell it that all that housekeeping information is now available to be read. Okay, so now next second comes along, you can just say, do that again, please. Okay, so it makes that whole operation very, very simple. So housekeeping, collection, or even setting up a series of particular commands can be just as simple as setting these up, having them set up beforehand in memory, and then just saying to the engine, okay, go. We've got 3 engines, so we can have 3 of these things going on at the same time through the various SpaceWire interfaces, if required. Okay, as well as supporting RMAP, we can support any other future protocol. So what we've got is each engine has a 3-channel DMA controller, which there's 3 transmit channels and 3 receive channels. And these are basically protocol selective DMA channels. So one of these will be triggered according to a particular protocol, and you can select the protocol that's going to be triggered by this. There's a protocol multiplexer which selects, detects the SpaceWire, or a particular SpaceWire protocol like RMAP, or a particular user protocol, and multiplexes the data recording accordingly. So it multiplexes it either to the DMA controllers or to the RMAP target or initiator. And we also have a SpaceWire timecode controller built into each of the engines as well. Okay, so this diagram just shows this. We've got the 8-port SpaceWire router and then the 3 SpaceWire engines with the protocol multiplexer, the RMAP target, the RMAP initiator, and then the 3-channel DMA controller. And then each of those engines goes onto the AHB bus and into the switch matrix to talk to memory, etc. Okay, so there's, as I said, there's a number of other peripherals. So we have CAN, mil standard 1553, etc. So there's a redundant pair of mil standard 1553 interfaces. These can act as bus controller or remote terminal. They have a DMA controller as well. There's a pair of redundant CAN bus interfaces which can support 15 channels. There's an Ethernet interface, and there's a number of lower speed peripherals as well. Okay, this just shows the structure of the lower speed peripherals. They all access through one port on the switch matrix. Okay, and each of the higher speed devices has a DMA controller attached to it. So to support software development, we have a debug port, which basically provides debug access and basic single-stepping, history trace, reading and writing to registers, memory, and so on. It provides all those capabilities. So we've got breakpoint, single-stepping, register memory access, trace memory, and hardware watch points as well. These features are accessible via JTAG, or debug UART, or for higher speed access via a SpaceWire port as well. So the Castor is being designed to operate over the full minus 55 to plus 125 degrees C temperature range. It will be around about 300k rads total dose, a good SEU error rate, and no latch up below a reasonable threshold there. The power consumption, we have, this is one of the critical design characteristics of this chip. So we've got dedicated mechanisms for adapting the power consumption depending upon the level of performance you actually require. So basically, if you don't require a particular function, you can actually switch the clock off to that function to save power. And in order to support the dynamic bringing in and out of various functions, there's a separate reset for each of those functions. So you can, say, bring up the SpaceWire interfaces, actually reset them, and then start running with them. You don't have to do a full reset of the chip. So with the current target that, for the operating power consumption is around about 5 milliamps per megahertz. So it should be reasonably low power power requirements. The software development environment, as I said, is being provided by STAR-Dundee, and we basically building this using the GNU compiler and obviously the hardware which is built into the chip itself. We've provided basically a monitor function which we've called Stargate, which allows you to access those on-chip debug capabilities. This supports the C and C++ languages. It's brought together in the Eclipse development platform with various plugins there. And we've also incorporated a technology called CodeRocket, which is basically a code visualization, a design and documentation tool. So that's integrated within the whole set of software. So just to mention CodeRocket, it's a fairly straightforward way of helping to do low-level software design and visualization. So we have this basically, and it's incorporated in the Eclipse environment. So you have 3 different views. So there's the code view down the bottom here. I don't know if I've got builds on this. Oops. There's a pseudocode view, and there's also a flowchart view. So this is the flowchart view, which basically shows a structured flowchart of the actual code itself. And if you're doing things like single stepping, as you single step through the code, so it will highlight where you are in the actual flowchart as well. So it's a very good way of getting orientated during debugging. This is the pseudocode view. So during design, if you want to sketch out a routine, you can literally just type in the pseudocode, and as you're doing that, it will actually draw the flowchart for you and then develop a code skeleton. You can then go into the code skeleton, start fleshing out your code, and as you do that, if you make some changes to the structure, it will automatically update the flowchart and the pseudocode. If you then want to do some modifications, you may want to move some blocks around in the flowchart, you can just grab those blocks, move them around, and it will drag the code around with it as well. So it's a useful way for just thinking about code, and also for showing this to non-expert stakeholders. So maybe for code reviews and so on. So rather than viewing the detailed code, people can actually review the flowcharts and the intent of that code as well. Okay, so this is basically showing that all the views are synchronized. So if you change the code, you update the flowcharts and vice versa. We've also incorporated to various other views within or various debugging views, so that you can actually look at the registers in the typical way. Okay, so you just get the hex value of various processor registers, but we've also incorporated a bit level view where you can actually see, okay, what each of the bits in a particular register means, and then you could go in and actually change those specific bits. So this actually makes debugging a lot easier. It just simplifies the visualization. Okay, so what sort of applications are we targeting with this particular processor device? So this shows a sort of fairly generic spacecraft data handling system and control and AOCS system. So, okay, so first of all, we have the instruments. So the chip is designed for low power consumption, but has plenty of processing capability. So you can actually use this in instruments that require low power and a moderate amount of processing power just by reducing the clock speed. If your instrument has demanding processing capability, then you can simply crank up the clock speed, and you've got that processing capability available. we've got a large amount of on-chip memory. So there's 1 megabyte of on-chip memory, which means for many instruments you'll actually be able to put all of the software into the on-chip memory and not need off-chip memory. We've got other on-chip peripherals and things like ADC and DAC interfaces for accessing the electronics of the instrument. We also have the interfaces to the SpaceWire network, and in particular SpaceWire RMAP target capability. So it's very easy to set up your instrument as an RMAP target and use that to configure, control, and actually read data back from the instrument. For more generic instrument processing, then we basically have that high processing power capability. So this could be for say, data compression or some particular instrument processing. So as I've said, we've got 150 MIPS, 40 megaflops of floating point capability. And again, the on-chip memory and the interfaces to the SpaceWire networks make the device ideal for that sort of application too. When we come to the mass memory, the fact that we've got SpaceWire and MIL-standard 1553 interfaces and a fair amount of on-chip memory for the command buffering makes the device very useful as the computer controlling the mass memory. We also have the on-chip SpaceWire router built in, so this many mass memory devices now have been designed using SpaceWire networks for routing between the memory modules of the mass memory. So this basically also provides one of the routing functions and a very simple way of getting those commands to all the various memory modules. And of course, the SpaceWire engines have DMA capability to simplify the data transfer. I've already talked about using the RMAP initiator for doing housekeeping functions. So it's perfect for doing that type of processing. And for things like AOCS, we've got the single and double precision floating point capability and interfaces which are suitable for most AOCS sensors, and including things like pulse width modulation for the actuators. So the device has been designed to cover as many different applications on board the spacecraft and have its power consumption and processing capability tuned, and in fact its interfaces that you've activated tuned to those particular applications. Okay, so where are we at the moment with this? This is actually our prototype device. It's implemented in an FPGA, and we have this running both in Dundee and in Nantes in France, where Atmo are working on this device. So the design's basically frozen. We're in the process of doing the final debugging and testing of the design before it goes to layout and then tape out for manufacture. Okay, so just to conclude here, it's the device will be called the AT6981 or Castor processor. It's a highly capable processing system on chip, low power, high performance. We've got substantial on-chip memory and an extensive set of on-chip peripherals. These include a SpaceWire router. I should say about the router, it's an 8-port SpaceWire router with 3 additional ports which go to the SpaceWire engine. So in fact, it's actually overall it's a 12-port router. 8 external ports, 3 to the engines, and 1 for system configuration. The chip is being designed to support spaceflight applications, and the current status, we've frozen the design, and we're expecting to have an evaluation kit available early next year. Okay, I think that's me. Any questions?
Questions?
There's one.
No.
Hi, Ken Peters, JPL. What characteristics of a user protocol can the protocol multiplexer be told to recognize?
Right, the key thing is the protocol identifier. So the generic SpaceWire protocol didn't worry about different protocols. It basically provided something that we could use for many different protocols. But then when we developed RMAP, we decided to put in two things. First of all, there's a requirement for a destination logical address, followed by the next byte would be a protocol identifier. So the key thing you would work on is that protocol identifier. But in fact, I think it actually looks at the first 4 bytes of the packet coming in. So you can multiplex on those and also multiplex on ranges of those parameters.
Do you have any missions that are early adopters of this processor?
At the moment, no. Okay. So, I mean, I guess we'll have adopters once we've got silicon that's been tested and validated. That's, but as I said, the current status is we're going to probably tape out towards the end of the first quarter next year, and the evaluation units will be available in FPGA form, we think, during that first quarter next year.
Okay. So, but typically, you think that this CPU would run an operating system like RTEMS or?
Absolutely, yeah.
Okay.
Yeah.
Just a quick question. How is the SpaceWire better or different than the Ethernet that you also have on the chip?
So let's repeat that. How is the SpaceWire better or different than Ethernet on the chip?
Okay, so SpaceWire in many ways is simpler. So SpaceWire is a very simple low-level protocol for communications. It runs at, typically in space implementations, spaceflight implementations, it runs at 200 megabits bidirectional. It carries a whole load of other space-related protocols. It can provide arbitrary architectures. The routing technology uses wormhole routing, which is low latency, and can provide arbitrary architectures. So I think in comparison to something like Ethernet, it's simpler, but basically does the same sort of job as Ethernet. But basically, the implementation is much simpler.
So it's lower latency?
Well, it certainly can be lower latency. We've also SpaceWire also includes things like timecode distribution as well, so you can just send time ticks over a SpaceWire network. The protocols that you provide on SpaceWire can be either very, very simple, or you can actually have more complex protocols, like the RMAP protocol that I presented there, which is very comprehensive protocol for doing the sort of things we do on spacecraft: reading, writing, configuration, control of instruments, accessing data from instruments, and so on. It's just designed to work on a spacecraft.
We have one more question.
Sure.
I was interested in your response to him that there are no early adopters. What, somebody's obviously investing a huge amount of money doing this. What drove this? Was there some need where you said, wow, this is our market, we've got to meet this need? I mean, because that's pretty risky, just saying we're going to offer a new processor with no demand.
So Atmel have a long history in developing flight processors. So if this was an Atmel presentation, you would have seen all of their previous history about their previous flight processors. So this is based on that sort of heritage. So I think the thing is, this is the next step in a long history of Atmel processors, like the 697, the 7913, so the ERC32. So that these processors are used on many missions in Europe, in the USA, and elsewhere in the world. So
this is the basket that they're going to put all their eggs in, kind of.
They will put their eggs in many baskets, I'm sure. But this is, in a way, it's the next step. It's okay, from just the basic CPU to a more integrated processor to now a complete system on chip, incorporating all the space wire technology. It's it's that additional level of integration. But the key thing there is to be able to meet those applications. We need to be able to tune the power consumption. So if an application doesn't need some of the peripherals, we can just switch them off, and you get low power. But then have that capability to switch those peripherals on when you need them, and you've got that integration. So it's mass saving, power saving, it's high performance, it's multiple applications.
Okay, very good. Okay, last one.
Okay. We have a lot of heritage with PowerPC and ARM-based ASICs and SBCs, and I'm wondering at a very high level, what are the discriminators that would make us want to go to a Leon-based?
Okay, so I guess certainly in Europe, the Leon processor is used quite widely, and I think in the USA and other places as well. So this is the next step in the Leon processor, and other processors are highly attractive as well, like the ARM and the PowerPC. This one, with the key thing I think we've got to hear is that complete system on chip, a large amount of on-chip memory, and it's for people that have been working with the Leon, then that's it can use that sort of code base, etc. So I think if you compare it to something like the PowerPC, then that's another alternative processor. With this device, it's the integration of the peripherals, it's the large amount of memory, and it's the ability to tune the power and the peripherals you're using to the particular application.
Okay, very good. Thank you.
Okay, thank you. If anybody's interested, I have some white papers here that describe the architecture in more detail, so you're welcome to grab me and get one of those.
Very good.
Thanks.
Our next speaker is